So, welcome to the final video of block 1 for TBMT42. It's the third video on nonlinear dynamics, and this time we will go to global bifurcations and chaos theory. And these are the things that are maybe the most evocative for the imagination. And they underlie things like statements of the butterfly effect, and related to these type of more complex behaviors, you also have fractals and chaotic attractors. So here we see a chaotic attractor. So here the system is just moving around here, and even though this is a stable attractor, so if you start away from it, you will move down to it. It never repeats itself, so it will move around in this attractor and it will never come back to the same place again. And if you start at 2 points that are very, very close to each other, as close as you want, then pretty soon they will start to diverge exponentially from each other, so that pretty soon they are at an arbitrary distance within this attractor. So this is one of the properties of chaotic attractors, and it's because of that you talk about this butterfly effect. That even if something as small as a butterfly is flagging its wing, flapping its wings, that little minuscule change will impact where you end up, if you end up here or if you end up here, and they are completely different. So that's the background to that statement. But let's get there and see how we get there. So global bifurcations. One of them that is central to biology is called the homoclinic bifurcation, and this is a global bifurcation that eliminates oscillations. So before the bifurcation, we have stable oscillations. So here we have towards this limit cycle here. And at the bifurcation, it's not a fixed point that is colliding with another fixed point, but it's a saddle point that is colliding with this limit cycle. And when this happens, then we call this a homoclinic orbit. And after the bifurcation, then the homoclinic orbit is no longer closed, so it stopped being a limit cycle, and then you don't have oscillations. It might look like it's going to go back to oscillations, but after a while of thinking, it will go away somewhere else, because it has become unstable. Limit cycle, you could say, or it's not a limit cycle. So, though these things happen in nature, well, they do. And we looked in a previous video on the Hodgkin-Huxley equation, and then I said that one of the things that you sometimes see in this type of electrophysiologically active cells, for instance beta cells, is that you have not only one action potential, but you have many. And this you see in all sorts of cells, and you also see it in models. So here we have many action potentials for a while, and then we have a quiescent phase, and then we have many oscillations again, then we have a quiescent phase. And this can be understood by slow variations in calcium, which goes up here during this time period and then down. And if we take calcium, the slow varying calcium, as a bifurcation parameter, then we can understand that we are actually moving here in this bursting region. So here the limit cycle appeared via Hopf bifurcation for much lower calcium values than we are at biologically, but they are always there as a potential. But over here, the limit cycle will run into a saddle point, and this saddle point is the same as the unstable fixed point that is the remains of the stable fixed point that was there before the Hopf bifurcation, but now it has undergone a sudden node bifurcation with another unstable fixed point, and it's this other unstable fixed point that meets up with the limit cycle. So it sort of has the seed of its undoing within itself down here. And if you're down here, then you the oscillations disappear. So this is sort of the end of the oscillations. And then if you move up here, you get back to the oscillations, and then if you move here, they disappear. So here we see a combination of different bifurcations, a Hopf bifurcation, a sudden node bifurcation, a homoclinic bifurcation, and another sudden node bifurcation. And they all appear when you change the calcium parameter. And that is, in this model, what generates this bursting behavior. This is how to explain why they are produced. So that's a fairly complex behavior, but it's nowhere near as complex as chaos. So here we have again a bifurcation diagram. So here we have a bifurcation parameter, and here we have a state X. So this is a Hopf bifurcation that you know what it is by now, supercritical Hopf bifurcation. And here we have a new type of bifurcation, which is again a global bifurcation. So here it's still oscillating, but here the period is doubled. So this is still the amplitude, but the amplitude doesn't go from, as it does here, from this value to this value, but it will go from this value to this value, and then it will go down to this value and this value, or some combination of that. So it will take two oscillations before it has passed both of the peaks and both of the valleys. So here the period of the oscillation has doubled. And here we have a new period doubling bifurcation, meaning that here it takes an even longer time before you have a repeating of the behavior again. Here it is still repeating. It's just that it will take quite many seemingly identical limit cycles before it actually becomes identical. And if you move along with this parameter here, you see that these period doubling bifurcations increase and they become more and more frequent. And eventually this goes into a mathematical phenomenon, which is that you have you reach a sort of limit, which means that there are regions here that if you start there, you will never repeat yourself. So it's not that you have sort of extended the limit cycle by period doublings. You are in a full chaotic attractor here. But then it disappears again. So you have these windows here where you again only have a slightly more complex limit cycle, and so on. So here you see, just by looking at this, that this is a very complex behavior that we see here, and here we have lots of chaotic regions. So this is one way to produce chaos. Does this appear in nature? Well, yes, it does. This was showed, for instance, in 2010 that, and also before that, that you have this type of period doubling bifurcation and chaos in hypertensive rat nephrons. So here we see experimental data, and here we see the corresponding period doubling bifurcation diagram for the corresponding mathematical model to describe this phenomenon. So finally, zooming out and sort of returning to reality and in even popular science. So this butterfly effect that I mentioned at the beginning is something that everybody knows, and everybody talks about chaos, but they don't really know what they're talking about often. And I want to point out some of these misconceptions so you can help to correct them. So as I said in the beginning, chaotic attractors they have a positive maximal Lyapunov exponent, and therefore they are divergent within the attractor. So no matter how close to each other you start, you will quickly diverge, and soon you will be at random distances within the chaotic attractor. So that is sort of the origin of the butterfly effect idea. But it's often misunderstood to say that, well, anything can happen because of that. And it's not true. You will always stay within the chaotic attractor. There are many situations where you have a chaotic attractor that's very, very narrow. So that even though within that attractor, you don't know where you will be in some fairly near future, and you can't predict it because you can't, there is no way of determining the initial condition accurately enough. You know that you will be within there and not anywhere else. So you will not end up in a random place in space. It's not sort of arbitrary what will happen. However, the existence, and here we sort of come back to philosophy and basic ideas of physics, which is what I come from and what I really like in life. It is important to realize that the existence of chaotic attractors, also in real biological systems, means from a fundamental point of view that the deterministic dream of perfect predictions, so just know the initial conditions and then you can predict any future, has been rendered impossible. It's not a realistic dream in practice. So no matter how good initial conditions you have, you will never be able to predict far into the future. And this has to do with also an inherent limitation to how well you can determine initial conditions. And this has to do with quantum mechanics. And quantum mechanics also has an inherent uncertainty built into it, and an inherent stochastic nature, random nature, which also renders determinism null and void from a principal point of view. So you see here that these type of things evokes the imagination and the thinking of sort of how reality actually is structured, and this is I think what good modeling and good science should do. It should raise the imagination. So with this little philosophical journey here at the end, we end the first block of the course, and in the next block we will do what they typically don't do in the chaos field, which is to apply data and really use data in a quantitative way. So that is what we will do in the next block.